Hello, good morning. Alright, so we are still in chapter 2. We are talking about the axial members, the analysis of axial members. Studying, the behavior of axial members would be very instructive in understanding the general problems, because the same principles may be applied to general problems in multiple dimensions too, even in inelasticity too. Okay, today's subject is non-mechanical deformation. That's the today's subject. Specifically, I'd like to talk about non-mechanical strain. Okay, non-mechanical strain. That's why the title of my current streaming service is non-mechanical strain. Alright, so let's talk about Hooke's law. Before we talk about Hooke's law, do you remember? I always emphasize that we have to use three laws, isn't it? Three conditions. The first one is equilibrium for force. Sorry about it. So we have to deal with the forces, and then here we have to deal with the stress, and then strain, and then displacement. Okay, so here in this direction, so we have to consider the so-called equilibrium. And then here in that direction, we have so-called constitutive law. And then here we need to deal with the compatibility, isn't it? Compatibility, displacement compatibility specifically. And also, instead of following this direction, so we may follow the other way too. So I told you that this is more general, okay? This is more general path of analysis. But here, this path is easy to understand. Okay, easy to understand. But for linear elastic system, so any approaches would produce the same result. So today we're gonna talk about here this point in more detail. That's what we want to talk about. Okay. Alright, so let's talk about the Hooke's law. So according to Hooke's law, the strain is proportional to the stress. Okay, that's the key point of Hooke's law. So to express this, we need a proportional coefficient. But in the graphical representation, the stress and strain, when we measure the behavior material, so when you apply stress to a certain specimen, so we apply the stress and supported on bottom here. Then if you measure the strain, we observe that the relation is almost linear, isn't it? That's the key point of the Hooke's law. And then the slope is nothing but just proportional coefficient in this relation. So according to Hooke's law, the stress is given by the elastic modulus times the strain. Or inversely, the strain is given by 1 of elastic modulus times the stress. Okay, let's talk about this relation in more detail here. Okay, this relation is applied, this relation is true only when the strain was caused by the stress. Okay, strain was caused by the stress. So if a certain strain is caused by the stress, then we have this relation. in the case of linear elasticity. That's the key point in understanding the Hooke's law. So what if there is another strain contribution, for example, by some temperature change? So now everybody understand that if there is any temperature change, strain increases or decreases. If temperature increases, then the material that I have usually for ordinary materials, the volume increases too. Okay, and we call it dilatancy. And then temperature drops, then the volume decreases, isn't it? That's why in the case of small strain, we can decompose the total strain like this. The total strain is equal to strain caused by stress and then strain caused by other effect rather than the stress. So we'd like to call it non-mechanical strain, okay? Non-mechanical strain. So it can be caused by temperature, or it can be caused by, for example, it can be caused by temperature change, or it can be caused by shrinkage of material, and that these two are called hygrothermal effect. Okay, and then also we'll talk about later, the same effect may be caused by misfit. Okay, 오차. So we have various reasons to have such kind of non-mechanical strain contribution. This is for the small strain. But what if we have large strain? In the case of large strain, the decomposition, the linear decomposition of strain is not valid, okay? Because we have highly nonlinear strain development. So in that case, we cannot use the linear decomposition of total strain. Instead, we can decompose the strain rate. Here, the dot in top of the characters representing the time derivative, okay? The rate of strain caused by stress plus the rate of strain caused by other effect rather than the stress is equal to the total strain rate. So here there is a point that you have to pay attention to. This is really very important. So in our discussion here, look at this. So we have to deal with these three conditions in any of our analysis. But here, let's look at here. If you look at here, after checking the constitutive law or material law, then we have to deal with the compatibility. So make sure the compatibility is the relation between the displacement and then strain compatible with the displacement field. Strain compatible with the displacement field. Now that's the role of displacement compatibility. So let's look at here. This is a total strain that we measure in the current, our structures or our solid mechanics systems under consideration. But here, this total strain, is composed of the strain from the stress and the strain from other effect. But let me ask you a question. Then if you want to discuss displacement compatibility, what strain that we have to use? What is compatible with the displacement field? 1, 2, and 3. So answer to my questions in the chatting window. By the way, how do you like my camera configuration today? So I little bit changed my camera configuration so that you can see my upper body, and also you can see my face better. So I have one response from Insa, 송인서, 호준이. And how about other students? 진영이 2. Christian 1. 호원이. Okay, good, very good. So you understand exactly the point. Very good, very nice. So please make sure that, you know, when we talk about the displacement comparability, the comparability condition is what the total strain that we can observe, and the displacement field that we think. That's the displacement comparability. Okay, that's the place where we have to apply the displacement comparability. So if you understand this point, the remaining stories is really straightforward. Okay, so no confusion. Okay, let's move to the next subject. So now let's look at this structure here. I have one-dimensional structure here, and then this one-dimensional structure, okay, is subjected to some temperature change. So if you measure the temperature change and the strain change, okay, let's prepare a specimen. Okay, specimen, and then I'd like to increase the temperature. This is the reference temperature. And typically the reference temperature is 25 degrees Celsius, and this temperature is assumed as reference, room temperature. This temperature is called room temperature. And then let's try to measure the strain change by the temperature change. And then what you can see is there is almost linear relation. Typically in the range, the temperature is less than 100 degrees Celsius in the case of concrete. Typically less than 100 degrees Celsius. And then there is a relation, linear relation, so 1. And then here the slope is measured by alpha. The name of alpha is thermal dilatation coefficient. So especially this is linear, thermal dilatation coefficient or thermal expansion coefficient. in 우리말 열팽창계수. Okay? 열팽창계수. Okay, this is the thermal dilatation relation. So let's imagine that, by the way, in this lecture note, so how do you calculate delta T, the elongation? So make sure that any strain is subjected to the displacement comparability. If there is no load, then the delta T is equal to what? The total strain times the original length. But here the strain is only caused by the temperature change. That's why here delta T is equal to epsilon T times the original length. And then how do you get the epsilon T? The epsilon T is equal to thermal dilatation coefficient times the temperature change, T minus current temperature minus the reference temperature. Simply we write that alpha delta T. So let's plug in here. Then this is alpha delta TL, isn't it? Okay. We can easily calculate the elongation caused by the temperature change. Okay, let's do a simple example here. So now I want to consider load 2. So here we have load, for example, let's apply the compressive force P here. And then I also have temperature change, delta T. Alright, so here I'd like to put A and B to understand, to figure out the nodes. So I want to use two different nodal points, point A and point B. And then before we start any analysis, so we need to put a coordinate system here. Then I can plot the displacement field. So here, because there is no load here, because there is no load in the member, so which means no load, and then the prismatic members and the semi-elastic modulus, which means the strain distribution is homogeneous, isn't it? That's why we can consider a straight line as the displacement distribution. So make sure that node A is fixed. That's why if you plot the displacement distribution, so node A is fixed, and here this is x coordinate, and then we'd like to call this is the length L here, and this is point A and point B. And then we have to consider certain kind of nodal displacement, UB. Distribution of displacement is straight. So as I told you, in the case of this straight line of the displacement distribution is equal to, the slope is the strain, the total strain. The total strain is subjected to what? The displacement compatibility, as I told you. Okay, so now we are here. So we are here. So we discussed the displacement distribution. Okay. So now let's talk about the strain. So my strain is equal to UB divided by the length L. This is my total strain. But now let's talk about the material law. So if you consider material law, my strain, the total strain, is the sum of strain caused by the stress and the strain caused by the temperature. And then here, here to use the constitutive law. So if I want to use constitutive law, the problem is the constitutive law is a relation between stress and strain, isn't it right? Stress and strain. So which means we have to transform the total strain to the strain related to the stress. So then the strain for the stress is equal to the total strain minus the thermal strain. Okay. So Hooke's law may be given by stress is equal to elastic modulus, and then the strain caused by stress is equal to elastic modulus total strain minus thermal strain. So generally speaking, so we may write in this way: elastic modulus the strain minus sum of all non-mechanical strain. This is the Hooke's law, where we include the non-mechanical strain here. Okay. So last time we had what? Hooke's law, the stress is equal to elastic modulus times strain. But make sure that this Hooke's law is extended to include non-mechanical strain with minus sign here. This is an important point that you need to understand. Okay? So now once you understand this, so we can consider the force equilibrium. Okay, So let's talk about the force equilibrium. So now let's assume that we have certain reaction. So we can calculate the reaction very easily, right? So here reaction is nothing but R, the magnitude of reaction R is equal to the magnitude of applied force P. So now we want to consider a free body diagram. So let's talk about the free body diagram. Okay, so let's talk about omega surrounding point B. If you do that, so free body diagram, omega. Then if you do that, I have body here, and then this is the cut surface, and then here point B is subjected to external force P. And then here we'd like to assume default stress field. Or please answer to me which one is correct, A and B. What distribution, which distribution is correct, A or B? So very good. It seems that you understand the concept clearly. So since we want to consider default stress distribution, so the stress field should stretch the material. That's why this is correct, right? Okay. So let's remove this. Okay. So now let's check the force equilibrium. If you check the force equilibrium, sum of all the forces in this direction should be equal to 0. So minus stress times the area, okay? And also minus applied force P is equal to 0. So let's plug the information of stress. Where is the information of stress? Information of stress is here. Information of stress is here. This is the information of stress of precisely speaking we have here, sorry. Okay, so let's plug in here. Then minus elastic modulus, and then I have cross-section area, and then strain minus the temperature strain, the thermal strain. So minus P is equal to 0. Then where is the information of the thermal strain? The thermal strain that depends on only the temperature change, the thermal dilatation alpha, and then delta T. And then how about the total strain? The total strain, it's subjected to the displacement comparability. Where is it? The total strain is subjected to displacement comparability. Here. UB divided by the length. So let's plug this information here. Then minus EA, elastic modulus and cross-section area, and the UB divided by length minus alpha delta T is equal to P. So you can calculate the nodal displacement UB, isn't it right? So you can calculate nodal displacement very easily because I have one equation and one unknown. Once you calculate the nodal displacement UB, then you can calculate the strain and then stress and other informations very, very easily, isn't it? So let's do one more example. One more very, very simple example. So I have a bar, one-dimensional bar. There's no load. But this bar is what? This bar is supported by two fixed ends. Okay, so we put the bar very tightly into the place. Then I'd like to say the point A and point B, and then this is my coordinate system X. But here I increase the temperature, delta T. So I want to increase the temperature. So what's going to happen? So temperature increases, the body try to expand by the temperature increase. Then it's going to push the support out, isn't it? Okay. So but the support wouldn't move at all. So which means the support would produce compressive force to the body, because the body wants to expand, but the support do not move. That's why we must have compressive stress in the body, isn't it? So let's check what happened here. So again, the procedure is still the same, okay? So here we have to consider the displacement field, the X and U. But here point A, the displacement is equal to 0. Point B, and displacement is equal to 0. Which means strain is equal to 0. How about the Hooke's law? The stress is equal to elastic modulus and strain minus the thermal strain. But here the strain is equal to 0. And how about the thermal strain? Thermal strain is alpha delta T. So let's plug in here. If you do that, elastic modulus, and this is equal to 0, and minus, and then alpha delta T. So here you can easily find out that we have negative stress by the temperature increase in the body. Okay, so if temperature increases, it's going to produce compressive stress in the body if the two ends of the body are fixed. Now what's going to happen if the temperature drops? Okay, temperature drops, then we have tensile stress. If delta T is minus negative, then we have the tensile stress distribution here. Okay, instead of temperature, let's consider humidity. The humidity is usually denoted by H. Humidity. Then in the case of porous materials like concrete, then if the humidity of the concrete drops, and then the concrete would shrink, the volume of the concrete shrinks. And if humidity increases, then the volume increases. Okay, let's consider the casting of concrete to a form of the concrete. Then usually, when you pour down the concrete is completely wet, isn't it? And then during the hydration reaction, then the pore space of concrete would lose the moisture. The water. The moisture drops. The humidity drops. Okay. Then humidity drops. Okay. Humidity drops, and then what's going to happen? Humidity drops. Then the material won't shrinks. That's why we have tensile stress inside the body. And then, but two ends are fixed, not to move. Then it's going to introduce tensile stress. If the tensile stress exceeds the tensile strength limit, then crack would develop. Okay. If humidity drops, then the shrinkage cracks develop. Such kind of crack is called shrinkage crack. Okay, and the shrinkage cracks are one of important subject to be discussed in concrete engineering. Okay. Okay, now let's talk about the misfit. the thermal strain and the shrinkage strain are not the only causes which produce non-mechanical strain. The pre-stressing technology would produce non-mechanical strains. Okay, let's talk about the pre-stressed concrete. Pre-stressed concrete members. Okay, let's consider this example. So what you wanna do in 우리말 is this is called prestressed concrete, or simply we call it PSC concrete or PSC members. The same meaning, okay? So now let's talk about a member here. So I have support, so still I want to consider one-dimensional member, and then I have member here, but I made a hole. This is the side view. I have a hole here, okay? So in the hole, I put a tendon. But not to the surface of this member. My tendon is little bit shorter than the length of the member. Let's say, for example, how do I call this? Say E. It is shorter than the length of the prestressed tendon is shorter than the length of the member. So as usual, we'd like to denote the length of the member is equal to length L. So please make sure that we are talking about the small deformation, okay? So now, but what do you want to do in the pre-stressing technology? We'd like to stretch the tip of the member, the tendon, what I mean. This is called tendon. In 우리말 긴장제. So we'd like to pull the end of the tendon so that this end of the tendon is in the same position as the surface of the member. Okay, basically we want to stretch out. Please make sure that if you stretch out the tendon and then you fix this end to the surface of the member, and this tendon would gonna compress the member, and then we must have the compressive stress in the member, isn't it? So let's check if it works. Okay, so initially we have non-mechanical strain here. So how do you measure this non-mechanical strain? So non-mechanical strain by the pre-stressing technology is equal to what? It is shorter than the length of the member by E. So which means this is smaller than. Then which means is this positive or negative? Positive or negative? So when you calculate the strain, okay, when you calculate strain, we always divide the elongation by the length. So now we have the tendon, which is shorter than the length of the member by E. So if I want to measure the strain of the tendon, so non-mechanical strain with strain of tendon, is it positive strain or negative strain? Positive or negative? Please answer to my question. Positive, usually positive, and then other opinions positive. Look, if temperature increases, the body expands, okay? The body increases, okay? Body increases from the reference, compared to the reference size of the volume, okay? Here, make sure that the reference size, reference dimension that we think is what? This is my reference dimension, okay? This is my reference dimension. This is my reference dimension. And then, but here in the prestressing technology, the tendon is shorter than the reference length. Are you still thinking that the pre-stretching strain is positive? Anybody who is thinking it should be a negative strain? Any other opinions? So make sure that the tendon is shorter than the reference dimension, so which means it has negative strain, okay? It has negative strain. Make sure that it's shorter than this. So minus the length difference divided by the length, okay? Okay, so now let's put, for our further analysis, I want to put A and B, denote this. And if you want, you can put some force P here. So let's check one by one. And then the distribution of displacement field, point A is fixed, point B, and then because point B is free, and then we may have a non-zero external force P. Let's say we have certain displacement UB, and then this is prismatic condition. So this is my displacement field. Alright, so now because we just designed the displacement field, now the next step is to calculate the corresponding strain, isn't it? The strain, here we have two different parts, the concrete and the tendon. The strain is equal to, but these two are, these two are in one piece. That's why the total strain should be same. Total strain is UB divided by the length. As usual, this is nothing but just slope of the displacement field. Now, let's talk about the stress in the concrete. The stress in the concrete is equal to elastic modulus of concrete, and then total strain minus any non-mechanical strain. Non-mechanical strain in concrete. Do we have any non-mechanical strain in concrete? Actually, there is no non-mechanical strain in concrete in the case of concrete, okay? And how about the tendon? In the case of PSC tendon, the elastic modulus of PSC tendon, and then we have the total strain minus the total, make sure the total strain is compatible with the displacement field, and then we need to consider the pre-stressing strain, and this is equal to strain minus, and then we already have minus sign, plus L over E, okay? And then let's replace, instead of strain, total strain, so we need to put UB and L. Here also UB and L. And somebody's calling me. Okay, so now let's check the free body diagram. If you check the free body diagram, so now let's talk about, now let's talk about this free body diagram here. Omega. Okay? So now let's talk about the free body diagram. So if you do that, the procedure is always simple. So we are following the same procedure always, okay? No difference. It's real easy, okay? So we have a rigid plate because I want to fix the end of tendon to the end of the member. And then we have the external load P here. And then I have stress of concrete. And also we have tendon. Okay. And then stress of tendon, sigma P. Okay, so let's check the free body diagram here. If you consider free body diagram, and then I want to check the force equilibrium. So sum of force is equal to 0. So let's check one by one. So we have positive force P here, and then I have sigma C. So minus sigma, look at that direction, okay? Sigma C times the stress of concrete times the area of concrete body, and then minus prestressing tendon, stress of prestressed tendon times the area of prestressing tendon. Okay, let's plug information of stress of concrete. The stress of concrete is here. So sigma C, if I rewrite sigma P, AP is equal to applied load P. This is elastic modulus of concrete, the area of concrete, times the strain of the total strain, so UB divided by the length. And now how about sigma P, the stress of tendon here? This is equal to elastic modulus of prestressed tendon, the area of prestressing tendon, and then here UB minus divided by the length L plus E and L is equal to P. So here let's finish the calculation. So if I finish the calculation, EC AC plus EP AP divided by the length, and then UB is equal to P minus so EP AP E over L. So my nodal displacement is equal to L divided by and then minus sorry about it, and then we need to put this term here. Okay, so let's check the characteristics of this equation. So what if there is no load? So what's going to happen if there is no load? If P is equal to 0, then because of minus sign, so UB is what? UB moves to the left-hand direction, isn't it? Yeah? Okay? Because of the effect of pre-stressing. And then let's consider further. UB, if without the force P, UB is negative, isn't it? Then if UB has negative value, then the stress of concrete is what? UB is negative, the stress is also negative. So which means if you apply the pre-stressing force to this member, so we can introduce compressive stress in this member. So make sure that the tensile strength of concrete is much smaller than the compressive strength of concrete. So by introducing this kind of pre-stressing force to concrete members, we can shift the origin or the reference position of stress-strain relation of concrete toward the compressive side. Okay? And this is the pre-stressing technology. Do you have any questions? So we talked about the temperature change, some moisture change, and the pre-stressing, and then as the sources of non-mechanical strain. And there are others too. For example, so we may consider bolt and turnbuckles. Okay, the bolt and turnbuckles. So if you put the bolt, if you fasten a bolt, then we have this kind of the length change. If you fasten the bolt, the length is shortened by the number of revolution times the pitch length. What would be the sign? Is it the strain caused by the bolt revolution, the nut revolution? Is its signs positive or negative? So make sure that if you increase the revolution of the nut, then bolt length decreases. But we're gonna fasten the bolt to the reference member. Is the non-mechanical strain of the bolt is positive or negative? I'm waiting. Yes, it's negative, okay? Negative. It's like pre-stressing technology, okay? The length is less than the reference dimension, okay? It's simply you think in that way. When we introduce the pre-stressing force to member, we stretch the pre-stressing tendon, and then we keep the end of pre-stressing tendon to the end of the member. But it makes the length, the original length of pre-stressed tendon shorter than the reference length. That's why it's going to produce a negative non-mechanical strain, okay? So negative is correct. Only Uchari gave me a correct answer. Okay. So this is a bolt, case of bolt, and in the case of turnbuckles. So if you apply one revolution to here, the turnbuckle, then the length change in two different directions. That's why here we multiply factor 2. Okay, this is pretty obvious. Okay, so next subject is stress and normal stress and shear stress in the arbitrary directions. So let me take about 10 minutes break, and then we'll be back. So we'll start the lecture at 11:25.